As for the peer teaching note from our group 6, we are going to present about the Cohen-Coon tuning method. This Cohen-Coon tuning method is basically a process reaction curve method for an open loop test. Cohen-Coon method is classified as an offline method for tuning, meaning that a step change can be introduced to the input once it is at the steady state. The output can be measured based on the time constant and the time delay, and this response can be used to evaluate the initial control parameters. The Cohen-Coon tuning has some rules where it uses three process characteristics, which are the process gain, K, dead time, and the time constant tau. The controller settings were determined using the following performance criteria, which is the 1/4 decay ratio, minimum offset, and minimum integral of the square error, which is ISE. Now, let's look at an open control loop block diagram. Okay, first of all, how can we identify it as an open control loop block diagram? Okay, the control system has been opened by disconnecting the controller from the final control element. So we can see here the final control element and the controller are disconnected. So this is considered to be an open control loop. Now, from this block diagram, we can get the transfer function process reaction curve between Ym and C. So we can get an equation for the GPRCS. Then it can be approximated with the help of the response of first order plus that time, where we can get the GPRCS equals to K e to exponent negative d to the power of 3 over tau s plus 1. And from the approximated model from the two, the values of the parameter K, that time, and time constant can be estimated. Gain is equals to B over A. This B stands for the output at steady state and the A stands for the input at steady state. And we can get the time constant equals to B over S, B steady state, and S where is the slope of the sigmoidal response at the point of inflection. Now, the dead time is equals to the time elapsed until the system responded. Let's look at these steps for finding PRC from step change response. First, we wait until the process reaches steady state. We record the process reaction curve. Then we introduce a step change in the input. And now, we will draw a tangent line to the response curve like this. Tangent line to the curve here at the point of inflection. Now, the apparent time delay, which is the TD, is the point where this straight line intersects the time axis, which is here. And you can get that K, tau, and TD with K equals to output over input, as I said previously, which is the B over A, and the TD or theta, where the time elapsed until the system responded, and the tau B over S. Then we find the Cohen-Coon controller setting based on the table beside this with the P, PI, and PID. With the use of first order plus that time model, we can get that P for Kc is equals to this equation. And for the with the use of PI, we can get for Kc and tau I. And at the PID, we can get the Kc, tau I, and tau D.
Hi, this is the advantages and disadvantages of Cohen-Coon tuning method. So the advantages are used for a system with time delay, quicker closed loop response time, while the disadvantages are unstable closed loop system can only be used for first order models including large process delays, and it is an offline method. This is the example for tuning feedback controller through process reaction curve. In this example, we examining how the dynamics of various typical processes influence the tuning results recommended by Cohen-Coon. So this is the graph, true and approximate process reaction curve for the multi-capacity process. Multi-capacity process is the process consists of two or more capacity in series. The approximate response is from the FOPDT. So the GP considered as two first order system in series, as you can see here, and the GM and GF is the first order dynamic of measuring device and the control valve. GPRC is in between of C and YM. So we can see that the transfer function of GPRC is KE negative TDS over tau S plus 1. This is because the same dynamic characteristic as the response of four first order system in series. This graph shows the process reaction curve for this value. First of all, you have to make the inflection point, which is the red one here, and then you have to draw the tangent line, which is this blue line. After that, you can find the slope, which is at the inflection point, which is 0.05, and the B is over here, which is 1, and the time constant is B over S, which that you find earlier, which is 1 over 0.05, which is 20, and that time is the tangent line that touch the x-axis, which is 2.5 over here, and the K is B over A. A is the input and B is the output, so the K is 1. And then you substitute the gain, that time, and time constant into the GPRC, and here is the transfer function. So using the Cohen-Coon suggested setting, we can find the proportional controller, proportional integral controller, and the proportional integral derivative controller. So that's all from me. Thank you.
Okay, moving on to Untitled Ziegler-Nichols method. During control design, preliminary controller settings are specified based on process knowledge, control objective, and prior experience. After a controller is installed, the preliminary setting set often proves to be satisfactory. But for critical control loop, the preliminary setting may have to be adjusted in order to achieve satisfactory control. Ziegler-Nichols is an iterative online to choose the value of KPI, KI, and KD. Online here means can do this adjustment directly to plant without needing a model. So we take a closed loop system consists PID control. UT here is a output function from the controller. Here we have a proportional integral and derivative term. From value of integral derivative is the value of KI and KD. A summary, KI equal to KP over TI and KD equal to KP times KD. For each procedure, first step is when the process has reached steady state, set KC equal to small value. Eliminate the integral and derivative control action by setting TD to 0 and TI to the largest possible value. Give KI, KD value equal to 0. Second step is increasing KC until it achieves neutral stability. Introduce set point and gradually increase value KC in small increment until continuous cycling occurs. The term continuous cycling refers to a sustained oscillation with a constant amplitude. Third step is record ultimate gain and ultimate period. Ku is ultimate gain, which is the numerical value of KC that produce continuously cycling. Pu is ultimate period, which is the period of the corresponding sustained oscillation. Final step is to find Kp, Ki, and Kd using table 12.6 in Seaborg book. For PID, here we got value of Kp. Ki can get by using equation discussed before. Ki equal to Kc over Ti, which is Ku and Pu we can get from here. And same goes to Kd. There are some advantages and disadvantages of this method. First, it does not require expert knowledge, means it not require a lot of understanding, like control system or dynamic system. And then it also does not require a model or simulation of the system. For disadvantages, it's time consuming. Why? Because if several trials are required and process dynamics are slow, the long experimental tests may result in a reduced production or poor production quality. Next, it could be hazardous. If external disturbance or process change occur during the test, because in many applications, continuous cycling is objectionable because the process is pushed to the stability limit. And lastly, it requires a stable system. Not applicable for unstable system because the closed loop system is unstable at both high and low value of Kc.
Alright, for the online Ziegler-Nichols usage example, Ziegler-Nichols is a interactive online to choose the value Kp, Ki and Kd. Okay, here our PID controller, here our function for this example, and here we can see our Kp, K proportional, Ki, K integral, and also Kd, K derivative. Okay, here example control tuning by Ziegler-Nichols user in MATLAB. First step, what we need to do is we need to start with small value of Kp, because here we want to use, we use trial and error method. We need to do trial and error. So we start with small value. So we want to start with small value of Kp first. And also we need to set our Ki, Kd equal to 0, because we want to run at proportional control mode only to find our neutral stability. So as I said, we start with our Kp value, so we increase our Kp value. For example, at Kp equal to 25, here we can see the response is not yet reach the neutral stability. So we keep increase our our Kp till we find the neutral stability. For example, here we find our Kp, our neutral stability at Kp equal to 60. So how we know we reach neutral stability? Basically, we see the peak of each oscillation is same height. Okay, from here, we know that our ultimate gain Ku equal to Kp at neutral stability. Also, we can find our Pu from the graph. Basically, Pu is the period here, ultimate period oscillation Pu, this peak to this peak. Also, what we take note here is Ku can be get from Rouse-Hurwitz stability criterion or simulation like we did, and as Pu can get from the response graph simulation, as I shown me before like this. Okay, after we get our Ku and Pu, basically we can proceed to the next stage, which we want to find our new Kp, new Ki, and new Kd. Basically, Ti, tau I or Td is tau D basically is to key in this formula to get our Ki and Kd. So after we get our Kp, Ki, and new Kd, we plug in here in our PID controller, and then we scope it. So here we can see the response. Here is the response basically from the Ziegler-Nichols method. Okay, here is some example from CC board, example 12.7 for Ziegler-Nichols method. Basically, we need to find our ultimate gain, ultimate period using trial and error. After, if we get our KCU and Pu, period oscillation and ultimate gain, basically we can apply our Ziegler-Nichols method. Okay, that's all from me.